Hi, everyone, and thanks for joining us. My name is Lauren Ballatin, and I work with the National Integrated Heat Health Information System based in NOAA's Climate Program Office. We're really excited to have everyone here for the session of the Heat Research webinar series. In today's webinar, we're going to be featuring projects supported by NOAA's Modeling, Analysis, Predictions, and Projections program. And the presentations will be discussing 3 research projects that have used advanced modeling, monitoring, and analysis techniques to translate research on heat into real-world applications and tools. Do stay tuned to the NOAA Climate Program Office website, where we'll be updating on future webinar series sessions. And in those future sessions, we'll cover topics related to heat resilience in urban, rural, and coastal environments, as well as local case studies. The series will showcase the breadth of research taking place, as well as the impact of these projects on science and services across the country. And on that note, registration is now open for the next webinar, which will be taking place on April 23rd at 1 p.m. Eastern. And that session will focus on NOAA-supported research that has advanced our understanding of compounding and cascading impacts of heat, with a focus on drought, air pollution, and wildfires. So if you're interested in joining us for that webinar, please scan the QR code on the screen and you can register for it. And one final announcement on logistics before we get started. We will have time for questions after each speaker's presentation. So as you listen, please feel free to type your questions into the Q&A box. And if comfortable, you can also add your name and your affiliation when submitting those. So I'll now turn it over to David Benson, my colleague, to introduce our first speaker.
Thanks, Lauren. Hi, everyone. I'm David Benson. I'm program staff with the MAPP program. And our first speaker for today is Dr. Kenneth Kunkel. And Dr. Kenneth Kunkel is an atmospheric science or research scholar with the North Carolina Institute for Climate Studies. He holds a BS degree in physics from Southern Illinois University and Master of Science and PhD degrees in meteorology from the University of Wisconsin-Madison. He has published widely on climate variability and change, particularly related to extreme weather and climate events. He is also a fellow of the American Meteorological Society. Thanks for being here, Dr. Kenneth Kunkel, and whenever you're ready, please begin your.
Yeah, thank you. Can you hear me okay? I'll assume that's a yes. Okay, so I'm going to be talking about this project here and century scale trends in humidity-based heat wave metrics. And the real focus of this talk is not the heat, it's the humidity, which we're all very familiar with that saying. And the reason that we worry about the humidity is that our bodies cool primarily through evaporation of perspiration. And when there's high atmospheric water content, this slows the evaporation and therefore the cooling rate and exacerbates the physiological effects of high temperatures. So if we look at historical trends in extreme heat metrics that are relevant to human health, we want to look in this project at century scale timescales that include the 1930s. And the reason for including the 1930s is that that period saw many all-time temperature records that still stand, particularly in the Great Plains and Midwest. And if you're wondering, well, how hot was it back then? And I would say, why don't you look at the historical data from Lincoln, Nebraska? Better yet, I'll show you the data from Lincoln, Nebraska. And here it is. And just to kind of orient you, this is daily high temperature for July 1936. The dark horizontal line shows 100 degrees. And if you look at that, you see that there were a lot of days above 100, and a number of those days were well above 100. In fact, there were 19 days greater than 100 degrees, 9 days that were greater than 105, and 3 days greater than 110. Lincoln set their all-time record on July 25th of that year, 115 degrees. That record still stands. And if you look at these data, it does kind of remind you of what if you looked at it without knowing where it came from, you might say, oh, it's probably from Phoenix or something like that. But this was Lincoln, Nebraska. At that time, Lincoln and the entire state of Nebraska, for that matter, much of the high plains and Midwest, was in severe to extreme drought. That month, with all these high temperatures, Lincoln had essentially no rain, 0.08 hundredths. If you look at historical pictures from the Dust Bowl era, it shows lots of areas that looked virtually barren. And my hypothesis is that humidity levels were very low, and that might have slightly mitigated the effects of these very high temperatures. So when we look at very long records, what's been available typically is temperature-only metrics to look at, well, how bad was it in the 1930s? Is there a trend in extreme heat? And generally, we've just had temperature to be able to look at that. And I want to show you just an example. This is a few years out of date now. I think the data goes through like 2021 or 2022. But this is one particular metric. I won't get into what it is for heat. And it shows time series going back to around 1900 for each of these regions. And if you just look at it, and particularly if you focus on the top part of this graph, which is the high plain or the northern plains and the Midwest, you see this peak right in the kind of the left-hand side of the graph. That's the 1930s. So in that region, the 1930s not only were high and record high, they stood above everything else in the record, at least according to this particular metric. If you look at the other regions, the East and the South, the 1930s kind of stick out a little bit, but not nearly as much. And then if you look at the West, the two time series on the far left, the 1930s maybe kind of showed up, but really the more recent period shows more extreme heat. So those are temperature only. Why are we only doing temperature if we look way back? Well, the problem is data availability. Humidity data have generally been unavailable in digital format before about 1948. If you wanted to look at times before 1948, all that you had available were paper forms. Now that has changed with the development of the National Center for Environmental Information's new Global Historical Climate Network hourly data set. So they have compiled information from the US and the globe into a single data set. And most importantly for this project, back in the early 2000s, there was a project to key data, put data in digital form from paper forms. And it did this for a wide variety of data sets. And the most important for this project was that they keyed hourly data from stations where they were collecting hourly data, such as wind speed, humidity, pressure, things like that were recorded. And the development of this data set brought that data into this single data set. And that's what we've been working with in this project. So the overall project goal is to develop humidity-based extreme heat indicators that span the period from the early 20th century up to the present time, and most particularly that it includes the Dust Bowl era. So we've been working on this, and our project started at the same time as that they were continuing work on the Global Historical Climatology Network hourly data. And there was quite a bit of data wrangling they were doing for the data set development, and we also were doing a lot of data wrangling in this project to get the data that we wanted. So we inventoried the data and identified stations with minimal missing data that included the 1930s. And so we developed this network, essentially a working set of stations that had data into the 1930s that covered the 1930s Dust Bowl era. Not all these stations have complete data during that period, but at least they have some data. So we developed and applied specialized QC tools ourselves. There's also a lot of QC that goes into GHCN hourly. And our own tools added some additional checks to identify and screen for errors, and also fill in short periods of missing data. We've computed hourly values of a suite of humidity-based extreme heat metrics. And what I'll be showing from now on, we looked further at this working set of stations and identified a subset of 26 stations with the most complete data. Now, the metric I will be showing today is the National Weather Service's heat index, and that's what they base their watches and warnings on if the forecasts are for the heat index to exceed certain thresholds. So I'm going to be showing you a whole bunch of graphs now, and the stations are grouped by region. I grouped them into 5 different regions across the U.S. The graphs, this particular metric that I'll be showing is the number of hours that the heat index exceeds the 98th percentile threshold for that station. And so these are annual time series, so there's a value for each year shown in a time series format. What you will notice immediately is that there's a lot of ups and downs. So at any particular station, some summers are very, very hot and other summers are not. So you see the primary thing you'll see is this up and down, a year-to-year variation. But what I want you to really focus on is the big picture. If you stand back from those graphs, does it show a trend? What features do you see? And I'll point those out. So let's jump in. First region I'm going to look at is the Western U.S. We have 4 different stations here. And if you stand back, you see this up and down. You see some big peaks in some of the stations. But overall, I think you can see that these stations are generally going up. And in fact, if we want to make a statement, there is a significant upward trend at all of these stations. Now, if you remember in the Western U.S., the temperature-only metric did not really show a strong signal in the 1930s, but they were showing upward trends. So this is consistent with that. We don't see the 1930s standing out here. We see some individual years that stand out at some of these stations. But the overall message here is that in terms of humidity based heat, the trend has been upward. Now I'm going to show you the largest contrast with this region, and that is the Midwest. So now I've got 6 stations here in the Midwest, good data. And if you look at those stations, there isn't much going on. And if we want to get a little bit deeper into that, there really is no upward trend in these stations. The 1930s remained prominent at least 4 of the 6 stations, the exceptions being Milwaukee and Chicago, but the other stations, you see the 1930s there if you look closely. This particular feature that you see here, we see no trend in extreme heat, is something that's been noted in many, many studies, including my own, sometimes referred to as the central U.S. warming hole. And if you just look at overall temperatures in the summertime, there's lack of a trend in temperature for this region of the country. And it shows up also in the extremes. And in this case, you see that here. There's essentially these graphs are flat. You can see some particular years here. I don't want to get into it, but if you look at Chicago, for example, the peak that you see there is the 1995 heat wave that killed over 700 people. Let's now move to the Northeast. The Northeast, we have 5 stations we looked at. It's kind of a mixed bag here. Most of these stations do not see a real trend, although there are some features that are interesting, and dig into those a little bit. The 1930s aren't really very prominent in these graphs. They weren't really that prominent in the temperature-only metric, and they're indeed not prominent here. Newark is one station that is going up. If you contrast that with Pittsburgh, which is not showing anything, it does represent a little bit the regional difference between those two. Pittsburgh is further west in this region, closer to the Midwest area where we've seen this lack of long-term warming. Here we have the southeastern U.S. Southeast U.S. is also an area that has not seen long-term temperature changes or very small temperature changes, and we do see this also in the southeast. If you look at these graphs, these are not going upward. They're for the most part. If we want to dig into it, if you look closely at these, the 1930s remain a prominent feature in the graphic. Other events also stand out. If you look closely at this, some of the large peaks you see at some of the stations is actually from 1980, which was characterized by a very extreme heat wave in kind of the southern U.S., a very long-running heat wave. And my final region is the southern plains of the U.S. Here, we do see that the stations, a lot of ups and downs. Again, I warned you that there were going to be lots of ups and downs, and indeed there are. And but these stations are tending to trend up. If you do a trend analysis, you find that these stations are going upward in trend. The 1930s do show up at some of these stations, not all of them, but the 1930s are exceeded by more recent events. At some of these stations, you will see a peak at 1980 in that particular event, but you see peaks in other years when there was extensive and extreme heat. So I would just add some closing thoughts here. The 1930s still stand out in our humidity-based metrics, but less prominently than in the temperature-based metrics we've been looking at. I think this particular data set and the metrics that we've calculated provide an important dimension to our understanding of trends in health impactful extreme heat. This is just some, we have more to do. The data are now in good shape, so we can really dig into some of the features, look at different metrics, understand how humidity, the magnitude of the humidity, inclusion of humidity, what that is having on the results. A couple more points here I'd like to make in terms of acknowledgement. There were many contributors to this work. I've listed them here. I hope I haven't forgotten someone here. I'd point out Ronnie Leeper here. In particular, he did much of the data analysis that I showed here. Matt Meny is in charge of GHCN hourly, so we had lots of coordination with Matt during this project. And finally, this was indeed supported by the Climate Program Office. I'm listing the grant number here, and the view I've presented here are those of myself and do not necessarily reflect those of NOAA. Thank you very much.
Thank you very much, Dr. Puckett, for a very interesting talk. We will now take questions at this time. So if anyone has a question, they can put it in the Q&A tab. One question is, you hypothesized that very low humidity during the 1930s might have slightly mitigated the impacts of those record high temperatures. How does this change our historical understanding of the Dust Bowl severity compared to like modern, more humid heat waves?
Well, I would say that one of the reasons why the 1930s Dust Bowl was created such high temperatures is for a variety of reasons. Extreme drought, which would have made the temperatures higher than they would have been otherwise. And I guess I would say something I haven't added here. Can we have something temperature-wise as bad in that area in the plains now than we did back then? And I would say the answer is no, mainly because of irrigation. There was no irrigation back then. Now there are a lot of the areas, including around Lincoln, Nebraska, there's lots of irrigation. It's virtually, I would say at least at the present time, impossible to get the kinds of temperatures we see in July 1936 now because of that. And of course, irrigation also humidifies the air. So the impacts on health might be just the same in a future, in heat waves, but it's because of the humidity, not the heat. Oh, I see a question here about absolute thresholds here.
Yes.
Yeah, we've actually done some analysis. I decided to show this one today. I didn't have that much time. We've actually done some absolute thresholds, particularly things like using the National Weather Service thresholds for heat watches and heat warnings, and they don't show anything that much different from what I shown today. But we do have those generated. We do have the data generated for those.
Okay, thanks. Thanks, Dr. Finkel. And for our audience, the question was, why not use an absolute threshold given that the physiologic effects are triggered on that basis? Thanks again for a very interesting presentation, and we'll move on to our second speaker. So our next speaker is Dr. Sean Millerad. Dr. Sean Millerad is a professor of meteorology at Embry-Riddle Aeronautical University in Daytona Beach, Florida. His research focuses on extreme weather events such as heat waves, floods, and severe weather. Most of his recent work examines humid heat trends and extremes, and the relationship of humid heat to marine heat waves and extreme precipitation in the southeast U.S. Dr. Milrad, thank you for being here, and looking forward to your presentation whenever you are ready.
Thank you. Well, thank you for having me. Today I'm going to talk to you about some work we've done, funded as well by the NOAA Climate Program Office and the MAPP program. Work we've done over the past few years developing a humid heat monitor for the southeast U.S. Based on wet bulb globe temperature. So just want to, a lot of co-authors on this, primarily folks at the North Carolina State Climate Office, both past and present. So Kathy Dello and Corey Davis, as well as Kyle Woodzicki at NCICS, and then some of my students as well who've worked on it over the past few years. This actually started, this work, the idea for this work started in a old school Twitter group chat between Kathy Dello, myself, and Jared Rennie, who's presenting next. So small world out there. Okay, just some motivation. Heat, as I'm sure most of you know, is the deadliest weather-related hazard in the U.S. You can see the 2024 NOAA weather fatalities there on the right, showing that heat far outpasses or surpasses all of other hazards. And that's true in most years. But also those counts are notoriously underestimated because a lot of heat-related deaths do not get counted as heat-related deaths. They get counted as respiratory distress or cardiovascular issues. So a lot of the best estimates we have are based on modeling. And there's some estimates of up to about 5,000 excess deaths in the US alone per year. Humid heat has been shown to have generally larger health impacts than dry heat, especially at night. That may be a little counterintuitive, but at night is when your body rests and kind of repairs itself. Humid heat, for people who do not have air conditioning, can really prevent sleep and recovery. Humid heat has been increasing in frequency, intensity, and duration across much of the world, particularly in humid climate locations such as the southeast U.S. But even at higher latitudes, we've generally seen an increase in humid heat severity and frequency over the past few decades. And vulnerable populations are extremely affected by this. This is not just people who lack access to cooling, but also people who lack transportation to cooling centers, things like that. And then one thing that doesn't get as much attention is people who have to labor outdoors, especially in the hot sun. Agricultural workers are often some of the biggest groups that have to deal with that on a regular basis. Human health, in terms of human health, humid heat can affect both physical and mental health. There have been a lot of studies on physical health, but there have been an increasing number of studies on mental health. Things that how humid heat can affect dementia, people with pre-existing mental health conditions such as depression and anxiety, and things like that. So it's a multifaceted health impacts. And again, that issue of outdoor workers, particularly farm workers and agricultural workers, they basically are much more susceptible to death from humid heat. They have died of heat related causes 20 times more frequently than other occupations. And protections for farm workers vary widely by state. For example, in Florida, despite it being a top 3 farm worker state, it really has no statewide heat protection regulations. It's a very different story in the West, especially in California, Oregon, and Washington. So it does vary widely across the country. In terms of humid heat impacts, there have been a lot of new heat products that have come out, many of them very good. Here is one called Heat Risk, which the NWS has been rolling out over the past few years. Won't go too much into this, but it's a categorical-based severity scale. Does a really nice job in the West, which is kind of where it was developed. And it is temperature only. Now, they do sort of indirectly incorporate humidity in this process, basically by measuring how unusually warm the overnight temperatures are, but they don't explicitly take humidity into account. So that was one thing we were looking to do, was to explicitly take humidity into account. And again, that's more important in a place like the Southeast U.S. Than in the Southwest or the Western U.S., where obviously it's a lot drier climate. In terms of humid heat, measuring humid heat, the metric you're probably most familiar with is the NWS heat index, which of course combines temperature and humidity. One thing to keep in mind about that, by definition, things like heat index are calculated in the shade, because both temperature and humidity are measured in the shade at most of our stations, certainly our operational stations. So to assess the full impacts of humid heat on the human body, you really need to incorporate solar radiation and wind speed in addition to temperature and humidity. And so the metric that really best does that is wet bulb globe temperature. This is not a new metric. It's been around since the 1950s. It was originally developed by the U.S. military. It is still used very much by the U.S. military. It's also used by OSHA and other occupational health and safety endeavors, and a lot of scholastic athletic organizations use it as well. The advantage is that it incorporates solar radiation in particular, but also wind speed, as well as temperature and humidity. The disadvantages are that it's tough to measure because it's expensive. You need specialized equipment, in particular black globe thermometers, as well as solar radiometers. And so that's, of course, not standard at things like ASOS stations, things like that. There are estimation formulas that can get around that, but they are subject to regional differences and error. And the severity scale that's been developed for wet bulb globe temperature is not necessarily intuitive, especially if you're used to heat index. So on that note, on the left is the heat index scale, and then on the right is the OSHA wet bulb globe temperature severity scale. So by OSHA definition, extreme wet bulb globe temperature is anything over 90 Fahrenheit, which is fine in a vacuum. But when you think about people and how they think about heat index, they probably don't even pay attention in a lot of cases until the heat index is at least 100. So if you were to switch the scale and say, okay, well, the most extreme heat is going to be when wet bulb globe temperature is 90, that's going to take some getting used to, right? Getting used to a new scale. The other thing about these wet bulb globe temperature thresholds on the right, and Jared, I'm sort of preaching to the choir here, is they are absolute thresholds, which are fine if you're comparing places that are kind of on the same playing field. But for example, if you're comparing Asheville and New Orleans, right, an elevated location with a much drier, cooler climate versus a location right by the Gulf. There, much more humid at sea level or below, acclimation is going to be very different between those situations. So we had to deal with that when we were talking about the entire Southeast. The first part of this work was really going through a bunch of estimation formulas and seeing which one worked best for our region. Wet bulb globe temperature is composed of 3 things: 70% natural wet bulb temperature, 20% black globe, and 10% air temperature. So we went through a few of these estimation formulas. We used 2 verification data sets. One was based on what is essentially the North Carolina State Mesonet called EcoNet. Those stations have black globe thermometers and solar radiometers. And then we also worked with a group within the U.S. military, the Range Commanders Council meteorology group, where they helped us give us their 1 year of field data campaign at various military bases within the Southeast. We were able to verify some of these estimation formulas. So here's just a picture of EcoNet and what their dashboard looks like. This is publicly available data on a regular basis. You can get it in real time. But these stations have black globe thermometers and solar radiometers. And then here's some of the initial work we did. I highlight so we evaluated 3 estimation formulas in our articles there on the left. We found that the Liljegren estimation formula, which is one of the better known ones for wet bulb globe temperature, was the best in terms of mean absolute error, as well as root mean square error. One of the other formulas, the Bernard method, actually was better for black globe temperature. But since natural wet bulb is 70% of wet bulb globe temperature, the Liljegren method ended up being a little bit more accurate in the Southeast because it was better for natural wet bulb. So we went ahead and used that for most of our trend studies, although we evaluated several throughout this process. So just before I get to the trends, we did this in a couple different ways. First, we did it with station data using the NOAA ISD, which is the precursor to GHCN hourly. And then we did it also in gridded basis using ERA5 land, which has a 9-kilometer grid spacing. And then we used ERA5 at the coasts just to make sure we got the entire region. When you calculate wet bulb globe temperature, you want to use wind speed data at 2 meters. So you have to logarithmically adjust the wind speed down to 2 meters. Kyle Wojcicki at NCICS developed a really nice custom Python package to calculate wet bulb globe temperature, taking all these things into account with all the different estimation formulas. You can get it at his GitHub linked right there. And then we started looking at the trends. So to get the trends, we first calculated the hourly wet bulb globe temperatures. We calculated daily max, min, and mean from the hourly data. So we started with hourly, then went to daily, and then the summer averages and extremes were calculated from the daily. We also did it for other seasons, particularly spring and autumn, but I'm only going to show summer results here. So the trends you will see are linear regression. The statistical significance was evaluated using the Mann-Kendall test, which is a common non-parametric test. The 99% confidence level is what you'll see hatched on the trends. I'm going to focus on daily min and daily max. As well as you're going to see some plots for trends in extremes. We defined extreme as the 90th percentile value. We did try other percentiles, and the results were fairly similar. The gridded results you can find in the second paper listed here. The station-based results are also in that Wojcicki paper from 2024. So daytime trends will be on the left, nighttime trends on the right. This is just intensity. One thing that pops out here, the scales are the same, is that the nighttime trends are larger in almost throughout the entire region. You see very large trends in parts of the Carolinas, as well as Arkansas and Louisiana. The daytime trends are significant in some places, particularly along the Atlantic coast and in Florida, but are not significant in a good portion of the Southeast, especially inland. Then we looked at frequency of extremes. So this is how often 90th percentile wet bulb globe occurs. And again, the nighttime trends were larger. In this case, the maxima were more located in Florida, especially central and southern Florida, as well as parts of Louisiana. Similar patterns in the daytime trends. It's just a big portion of the region. The trends were not significant and were considerably less than the nighttime trends. When you look at the station data, so this is just 2 examples. I have New Orleans at night on the left and Daytona Beach on the right for the daytime. This is, again, frequency of extremes. One thing you notice is that, especially within the last 10 years, the trends are not linear. It's fine to calculate linear trends, and they do tell you stuff. But, for example, since 2016, New Orleans has averaged 23 extreme nights per summer. That's about a quarter to a third of the summer. And similarly, since 2015, Daytona Beach has featured over 20 extreme days per summer. So again, that's about a quarter of the summer. So big escalation, especially since 2015, and that's one thing we've definitely noticed as we've been producing these trends. Duration has also increased, probably not as much as frequency of extremes, but again, you see those nighttime maxima in Florida and especially in parts of Louisiana. We think the Louisiana one might be in part related to a stronger low-level jet, but I didn't really have time to get into that in this presentation. Then we asked ourselves, okay, well, we know wet bulb globe temperature has these 4 components. What's causing the increase in the wet bulb globe temperatures? And the answer predominantly is dew point. So you'll see these are contributions to trends. You'll see the one on the right, a lot darker shades across most of the region. And that just shows that dew point is by far the biggest contributor to trends. Dew point and temperature were way above the other two. Of course, they're not all independent of each other. But dew point over most of the region is the largest contributor. The exception to that is the Appalachians, where temperature is a bigger contributor than dew point. One interesting thing is we also did this for Europe. Europe, a much drier, more mild climate, and temperature was by far the largest contributor in most of Europe. So the fact that dew point is the biggest contributor seems to have a lot to do with that you have a background, a warm, moist climate. All right, I want to talk about the product that's come out of this, or at least one of them. This is going to be called the Southeast Humid Heat Monitor. It will be operational later this year, probably within the next few months. You can access it at the link there. It is based on ERA 5 land and the ERA 5 gridded work we did. The testing and evaluation is still going on, but it was performed with 6 NWS WFOs as well as other partners throughout the region. Here is an example of the output. So you get a product where you get the forecast maximum wet bulb globe temperature. That comes from NDFD, NWS gridded product. You have the absolute thresholds in the colors that are highlighted there. And then you have the percentiles in kind of the hatching or shading over top. We're still kind of working with the color schemes and perfecting that. But you can see like 90th, 95th, 99th percentile are there right now. We're planning to add standard deviations. So basically you get a view where you're not only seeing the forecast wet bulb globe temperature for the next 3 days, but also how it fits in a historical context, both in terms of absolute thresholds as well as relative thresholds. So we're also planning to add other things to that product, messaging for exposure, sensitivity, and adaptive capacity elements. We'd certainly like to add objective metrics to that and perhaps make a categorical index along the lines of the U.S. Drought Monitor that kind of integrates those vulnerability metrics at some point. And my group is also working on looking at these humid heat compound hazards. So when humid heat overlaps with marine heat waves, especially in coastal areas, as well as extreme precipitation, because we think that basically humid heat events can prime the atmosphere for extreme precipitation that occurs at the end of the humid heat wave, so to speak. So if you have any questions, you can email me at any time. And I also have my link to my website and recent publications there, including the ones that I mentioned in this talk with the QR code. So thank you very much for your attention, and I'm happy to take any questions.
Thank you so much, Dr. Murad, for a very interesting talk. We probably have time for just one question. The Southeast U.S. Humid Heat Monitor that you just showed a slide or two before, could you just share briefly who the intended users for that application will be? Or if you already have it running, and if you have a sense of those who actually use this information.
Yeah, that's a really good question. So I would say there's a range of users across different sectors. The Weather Service has been very interested in this, in using it. Some of their messaging. Agriculture partners, especially within North Carolina, have been very involved, as well as public health entities and emergency managers. So it's intended to span the range of sectors. Yes, the public sector, but also the sort of applied sector in different industries. And we're hoping to not just agriculture, but also things like construction and outreach and groups. Athletics would be another group that I think would make good use of it. So we're hoping that it reaches. But that said, it definitely meant to reach people who are at least somewhat familiar with wet bulb globe temperature, and that spans the range from agriculture to occupational health and safety to athletics, and obviously the weather service and emergency managers as well.
That's great. Thank you very much.
Thank you.
All right, we'll move on to our final talk for this afternoon. And our final presenter is Jared Rennie. Jared Rennie is a research meteorologist for NOAA who sits on a treasure trove of data. Originally from Boston, he moved to Asheville in 2010 to perform climate research, primarily focusing on heat waves. Recently, he has shifted efforts towards science communication, bridging the gap between climate extremes and vulnerable communities. Really excited to listen to your talk, Jared. Thank you for being here, and whenever you're ready.
Yeah, thanks. So I can see. So someone is sharing my slides, so I'll just let you all know when to move forward. And I'm assuming y'all can hear me right now. So just a quick extra introduction to add a little bit of context and kind of link all three talks together. So I used to work for the North Carolina Institute for Climate Studies. So Dr. Kunkel's part of that now. In Dr. Milrad's talk, he talked about Kyle, who's done a lot of work. So I was when I was over in that realm, I was very interested in heat severity and heat trends and heat population. So I kind of worked with a lot of the PIs to kind of get, all this funding through MAPP to get this going. And then as soon as the funding calls went out and got accepted, I made the decision to switch over to federal workforce. So I had to sort of leave these projects behind. But I'm a super passionate about all this stuff. And what my talk is about is to try to find ways, at least on the federal side, to incorporate heat and also sort of the people that are affected by it. And so it is slow going, but we are still thinking about it. So yeah, I work specifically for the National Centers for Environmental Information. Basically, we archive your data and I play with it. Since I've been a federal employee, I've been working on multiple projects, including flooding and drought, but heat is still a passion of mine, and I will still keep screaming into the void to whoever wants to listen about heat trends and such. So thank you all for being here today. So let's go ahead and go to the next slide, please. All right, so I have a couple motivations, and you've already kind of heard a little bit about this in the earlier talks. So the first motivation is to try to integrate heat data with any other relevant data to kind of make people really care about it, because I work for NCI. So one of the things that we do is every month we have reports that go out that say, hey, it was the warmest year on record, and it keeps happening. We with every year we get in the top 2 years warm. Every month we'll say it was the warmest winter, it was the warmest January, it was the warmest February. And it's very good reports. I really highly suggest that you go and take a look at it. But over time, we start to get maybe sometimes fatigued about hearing it over and over again. And it kind of comes back to, well, why should I care? Well, I think we all know that there is a social component to it, and then there's also an economic component to it. So, social data, and that's what the bulk of this is going to be about. But how can we just taking population data from the Census Bureau and say like, hey, it may not have been the warmest year on record. It could have been like the 7th warmest year on record. But there are many counties, many census tracts in which people are still affected by having top 5, top 2 heat. So there's plenty of data sets out there that we can look at. So obviously NOAA is under the Department of Commerce. So is the Census Bureau. So they have their 10-year census that comes out, but they also do estimates every year. Through something called ACS. And there's other stuff as well, which I'll get into. The CDC has something called the Social Vulnerability Index. FEMA actually released something last December called the National Risk Index, which has a heat component to it. So, and a lot of those indices use NOAA and Weather Service data. So it's a good way of complementing everything. And again, to get a sense of who's being affected by these events. The other thing, economic data. So there is, NCI at one point had billion-dollar disasters. It has since been decommissioned from NOAA, but it's been taken up by Climate Central, and they analyze events and try to add a number component to it to say, are these costing money? I mean, the short answer is yes. So that particular data set looks at more extreme cases like hurricanes and flooding, tornadoes, but they do talk about drought and heat as well. So, and they've also toyed the idea of having, $100 million disasters, because if it hits $999 million, it's not documented, but one would argue that maybe it should still be noted. So the goal here is, the motivation is to try to do a lot of this integration. So go to the next slide, please. So this animation, which yes, it is working. Excellent. So this is something that I produced, and this is raw NCEI data. So this is every month as you progress through the year. So this is, it first starts off as just the January value, and then it's the year-to-date temperature ranks as you go throughout the year. And obviously, there's a big spatial component to this. So again, I don't know what the numbers were off the top of my head. Certainly a top 5 year for the US in all of 2025. But as you kind of get to the end of the graphic right about here, you'll see parts of the Western US are, have higher rankings than other places. So this is just kind of a quick, easy spatial join of just slapping together some population data, and we can say like, hey, we had about 100 million American, citizens that, experience a top 10, if not warmest heat out west. So just adding something like that would just, put a little extra context to, who's being affected by these events. We can take a step further if you go to the next slide. So this is the CDC Social Vulnerability Index. This is the version from 2020. I think they've updated it out to 2022. And we can basically, for the GIS nerds in the room, we just do a spatial join and go to the next slide. And now you're only seeing counties light up that experience a top 10 warm year with each month of the year, but also have high vulnerability. So CDC's definition of high vulnerability means that folks have a harder time recovering from disaster. So CDC's definition of a disaster is probably different than NOAA's definition. So CDC's definition is like, it doesn't have to be weather related. It could be COVID, it could be mosquitoes, it could be West Nile virus, different outbreaks. But nonetheless, it's a good starting point to kind of showcase, which counties, or we can do census tracts as well, by the way. It's just a little harder to show on the map here, but which particular areas are having problems with heat. And, this can be a good, NCI is very retrospective. So we're after the fact, after the event happens, we analyze it. But I could also see this has good forecasting abilities. So when the Weather Service, even right now, there's big heat out in the West right now, and it's forecasted to be pretty hot. So, what areas should folks like emergency managers, Weather Service employees, what areas should they be looking at? And we can kind of look to the past to help forecast the future. Next slide. This is just another way to visualize the same thing. This is a bivariate map. So for those that are not only GIS nerds, but also Esri nerds, they're very big on this type of stuff. So it's kind of like a 2-dimensional axis. So, sort of on the x-axis is the actual ranking from NCI, and then the vertical axis is the social vulnerability. So you can kind of pinpoint it. This is kind of like one of those old 1990 Magic Eye things where you have to stare at it for 5 minutes to really get what's going on, but really provide some good context again as to who's vulnerable in certain areas. Next slide, please. So that is the CDC's version. And I had mentioned that it's not weather specific. So I mentioned we're part of the Census Bureau, we're part of the Department of Commerce. So the Census Bureau is as well. They actually produce something. They kind of produce their own vulnerability index. They call it the Community Resilience Estimate. They have it's the same concept where you're taking individual variables, throwing it into some sort of principal component analysis, and then you're spitting out sort of numbers or adding those components up and getting a risk value or an estimate. But a couple of years ago, they did one specifically for heat, which I thought was really interesting. So I kind of harped on them and kind of helped refine all these little risk factors that they have. So this is actually an older version of the risk factors, but I'll just briefly talk about some of them. Housing, that's obviously a big deal. Communication barrier. So if the Weather Service forecast is in English, let's say, if you're Spanish speaking or Mandarin speaking, you may not have that information. Also, they add a lot of economic component in here. What's the sort of income, disability. Obviously, we know that heat affects older folks more, disabled folks, kids, things like that. So they actually have, I believe in their newest version, they actually have 11 different risk factors. And one of the things they were able to estimate is access to air conditioning, which I think is almost like really important because one, not everybody can afford air conditioners to be on all month. There are folks with people with lower socioeconomic status. Sometimes they do have to decide whether or not to pay their electric bill or to pay for groceries or gas or what have you. So they have to make those decisions. But then also you think about areas like the Pacific Northwest or northern New England, where maybe 30 years ago you didn't even need air conditioning, but now you do because of the increasing trends in both temperature and humidity. So that in the new version, they actually have incorporated that, which I think is really a game changer. Go to the next slide, please. Thank you. So this is the map I showed earlier. So this is again counties with high vulnerability from CDC and the top 10 ranked. But go to the next slide. So now you're seeing, different areas kind of stick out, especially I think in some of the cases, the Pacific Northwest and northern Maine stick out a little bit more in some of the months because again, it has that extra component specifically related to heat. We produce these reports every month internally. Some of the information gets put out into the monthly report, but we have partners that are very interested in this kind of work. And given that we're kind of working with the Census Bureau to refine these models. Okay, so next slide, please. So that's sort of the first motivation, is to try to understand, who's being affected by heat. The second motivation is literally my number one rant of all time. Dr. Milrad did hint at it a few minutes ago, and I apologize. I will be bringing it up again. So my number one rant of all time is I work for NOAA, so I have to be nice to my weather service partners. However, when I was doing some heat research, when I was with the North Carolina Institute here, I was very interested in heat in North Carolina, obviously. And I was just for fun, let's just see how many heat advisories were issued for the state of North Carolina. And this graphic got produced, and I was stunned. And my mouth dropped open. And the reason why is because now you won't be able to really see what I'm talking about, but I'll try to explain it. So I live in the western part of the state. So I live in Asheville, North Carolina, which is in Buncombe County. It's one of the counties that are in white. And I was shocked to find out that we had between 1986 and when I generated this, so this was back in 2020, but still true to this day, Buncombe County has never, ever, 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 ever had a heat advisory. And I was like, okay, we're in the mountains. I get that. However, that seems impossible. And the reason why that's the case is that the National Weather Service, and anywhere in the state of North Carolina, you have to have a heat index of 105 in order to get a heat advisory. Well, the highest heat index at Asheville Airport ever recorded was 102. So does that mean we don't ever have heat issues? I would argue that's wrong. And using absolute thresholds can be very problematic for this particular reason, because there are geographic, there are elevation, and there's also many different issues that go into this. So it's been a big motivation of mine. I do think a lot of the work that the previous folks were talking about, Dr. Kunkel, Dr. Milrad, they're doing great stuff. I will concede that in some cases that you may want absolute thresholds. Okay, fine. But having relative thresholds like the 98th percentile, I think is super important. So go to the next slide. So this kind of links up to something that was already talked about, but I'm a huge fan of heat risk. Again, it's a Weather Service product. It was initially out west. It is national. It really takes into account the climatological and elevation effects and geographical stuff of heat. I think it's super important because, again, I think that, a 90-degree day here in Nashville is way different than a 90-degree day in Miami. Next slide. I'm gonna kind of go over these pretty quickly, but another good reason for this is because of the fact that there's different thresholds of what these colors mean. There's been social scientists that have been helping to kind of dictate what these numbers mean, which is a big thing in our field right now. Go to the next slide. Yeah, so these are just some animations. So this is heat risk the first week it came out, just rolling through each day. Go to the next slide, please. Yeah, so this is kind of the same concept as before of like, okay, now show me, instead of just showing top 10 warm heat, show me areas which have a high heat risk for that given day, but also are considered have those high CRE, the community resilience for estimate heat values. So again, pretty the spatially big for these because it's county level and such, and heat is generally very large in synoptic scale. Go to the next slide. This is specifically for North Carolina, so you can start to see, certain areas down by Charleston, down on the coast, and then of course Western North Carolina. See, they fall into okay, they have moderate heat for this day and have high, essentially high risk for heat. So this is something that weather service offices and state climate offices can use to kind of pinpoint those neighborhoods that could have issues. Next slide. I'll just quickly go over this one. This is just another event that was in Texas. Again, showing that with the census tracts, you can, especially in Texas, you could have thousands of census tracts. So what would be super nice for the future is to have some sort of interactive thing here, so people can kind of zoom in and get to their particular neighborhood. Next slide, please. And then just finally, this is my second to last slide. The fact that they're using climatological information is great. So this is specifically for Asheville Airport, which I'm not too far from right now. And depending on the time of year, what are the different heat risk thresholds? Because again, for us, just kind of squinting here, it looks like 92 would put us, in a pretty high level, but that number could be 102 down the mountain in like Charlotte or Raleigh, let's say. So a lot of great work being done by folks in the Weather Service. What they're doing right now is they're trying to refine heat risk a little bit, because in the back end, it's using some data from the CDC. So it's using heat morbidity data. And those regions that they use are the CDC regions, which are very, very large. So people are trying to do localized validation of it. I know some offices in, I believe, South Carolina and Mobile, Alabama, they're trying to look into that. So it's just kind of making it a little bit more refined and better. All right, next slide. And then I'd be remiss to bring this up. So all the talks so far, talked about humidity. So I have to talk about humidity just a little bit. So heat risk and the data that NCI provides right now are really only based on temperature. But I am 100% in the camp with Dr. Kunkel and Dr. Milrad that it's not the heat, it's the humidity. I very much despise the humidity. I literally made my own index called the Jared is Miserable Index, which is basically, it's a super scientific, super peer reviewed, by me at least, method of tracking humidity. So whenever the dew point's over 55 degrees, I'm miserable. And whenever the dew point's over 70, you have to leave me alone. So I'm hoping to incorporate this into more operational models at NCEI. I couldn't say that with a straight face. But anyways, humidity is such a huge factor for our operations. And I'm a huge component of wet bulb globe temperature. So don't use this, use wet bulb globe temperature. I'll leave it at that. Thanks.
Thanks so much, Jared. Very interesting. We only have time for maybe one question, so I will. We have a few questions here, so I will just take the first one here. Beyond the social vulnerability index, have you explored how people's inherent adaptability to extreme temperature varies globally? For instance, hot regions may adapt more easily to rising temperatures than northern areas lacking AC or heat resilience.
Yeah, that's a great question. I have not specifically looked into that, but I'm obviously there are especially in a global sense, some folks are more adept to different heat extremes, and I had mentioned social science earlier. We're just, especially at NOAA, we're just trying to get the grasp of throwing social science at a lot of this, and it comes from different levels. The first level is like, do these graphics make sense? Are they the right color scale? Are they in compliance. But yeah, it does come back to the physical question of, what does a 90-degree, 95-degree day mean to you? Or if you're told to, seek shelter or don't go outside, what would you specifically do? So and of course, a lot of I really didn't show any trend stuff here, but as we know, there are, what we see now will most likely be different in 5-10 years, if not to the end of the century. So adding that perception as well is super important.
Thanks again, Jared. Thanks so much for a very interesting talk. And there's one question there about air quality, and our next webinar will be on heat and air quality. So maybe your questions will be answered in that webinar. I'll pass it back to Lauren. Thank you.
Thanks, David. Just want to say thank you to everyone in the audience for joining us today, and also a big thank you to Ken, Sean, and Jared, our speakers, for their wonderful presentations, and of course our 2 sign language interpreters. This webinar is being recorded, and it will be posted on the NOAA Climate Program Office website within a few days. And again, you can see on the QR code on the screen, registration is open for the next webinar in the series. So please join us on April 23rd at 1 p.m. Eastern to learn about the compounding and cascading impacts of heat. We'll be showcasing research on heat and its connection with drought, air pollution, and wildfires. So just to wrap up, thanks again to all the speakers. Thank you for attending, and looking forward to seeing you next time.